Hello everyone, my name is Ganga Jayaratna. I am an online master student in electrical and computer engineering at Purdue. Also, I am a member of the Quantum Game Club and I became interested in quantum computing in the second semester of my grad studies because it seems very exciting for me and I would like to share some of my learning experiences so far with you all. The purpose of this video is to give you a basic introduction to quantum programming using Qiskit, which is an open source development kit introduced by IBM. Qiskit provides tools for creating and manipulating quantum programs, and you could run your program on real quantum devices on IBM or run your program on simulators on your local computer, which means that the Qiskit toolbox allows you to write codes in Python on your computer and send those to a real quantum computer to get results. So Qiskit makes it easy for anyone to use quantum computers regardless of your skill level or your subject area. And I hope you will get some advantage from this and join us to explore the world of quantum computing. This is the outline of my presentation. The first part of this video includes a basic introduction of quantum computing, a quantum bit and why it is so important to us. Also quantum gates and how they work. And one thing I need to mention here is you don't need to have a quantum mechanical background to learn quantum computing, but something I learned is that you need some quantum concepts to understand why you do certain steps in quantum computing. The second part of this video includes the basic instructions to access Qiskit through your local computer or access through IBM Quantum Lab. For cloud-based access, you need to create a free IBM account. In the third part of this video, I will explain how to write a simple quantum program using quantum gates and run it on the local simulator and then run it on the actual quantum computer in IBM. Also, the resources available for you if you are interested in learning further about Qiskit programming or quantum computing. This is a picture of a quantum computer sitting in IBM lab. This is the first part of the video. As I said, this section includes some key information that we need to understand quantum programming. If we compare the classical and quantum approach, in classical computer we use 0 and 1 or transistor on or off states. When the current passing through the transistor, we consider it is in state 1, and when the transistor blocks the current, we consider it is in state 0. However, in quantum computers, we use the fundamental unit is quantum bit, which is qubit. The quantum computers are designed to use the properties of quantum mechanics such as quantum superposition and quantum entanglement. Quantum superpositions means that a qubit can represent state 0 and state 1 or both at the same time. For example, if we consider the state of an electron, it could be in spin up and spin down polarization states at the same time. This special feature gives the ability to process every possible answer simultaneously and resolve certain problems more quickly than classical computers. In a classical computer, the information processing is carried out by logic gates and the circuit behavior is governed by classical physics. But in quantum computers, the information processing is carried out by quantum logic gates and the behavior is based on the quantum mechanics. Therefore, we need to learn how quantum gates work in order to write a quantum program. Also, classical programs have low error rates and they can operate at room temperature. However, quantum computers operate at very low temperatures and also they are extremely sensitive to noise. So the error rates are very high. Actually, these are the challenges in building a reliable quantum computer. But for now, we just focused on understanding qubit and quantum gates. Let's introduce some notations to distinguish quantum states from classical states. Qubit has two basis states, ket 0 and ket 1. This is the Dirac notation, which is the standard notation for states in quantum mechanics. We can represent this ket 0 state as vector 1, 0 and ket1 state as vector 0, 1. These two vectors are orthogonal to each other, therefore we can represent any two-dimensional vector with a combination of these two states. So the state of a qubit can be written as state psi equal to alpha ket0 plus beta ket1. Here alpha and beta are complex numbers. This state vector psi is described by a linear combination of the two basis vectors 0 and 1. Before we perform a measurement, qubit can be in both 0 and 1 states, but after we measure, it collapses into either 0 or 1. So the probability of obtaining state ket 0 is alpha squared, and the probability of obtaining state ket 1 is beta squared. Obviously, the total probability should be equal to 1. This is a geometrical representation of a qubit. This is called Bloch sphere. The top of the Bloch sphere, I mean the north pole, represents ket 0 state. Here we have a 100% chance of being in the state ket 0, and the south pole represents ket 1 state with a 100% chance of being in state 1. The surface of the sphere represents all the pure states of two-dimensional quantum system, and the points inside the sphere correspond to all the mixed states. Plus state is formed by the equal superposition of ket 0 and ket 1. It's pointing towards the positive x direction, and this is the minus state, which is pointing towards the negative x direction inside the Bloch sphere. With that introduction of qubit states, we now move to quantum gates. In classical computers, we use classical logic gates to build digital circuits. Similar to that, we use quantum logic gates as building blocks in quantum circuits. This section I will briefly explain few important quantum gates. This is an example of a quantum circuit. It includes inputs, outputs, and the symbols used for operations. Quantum gates are reversible. These reversible gates can be represented as matrices. The most common quantum gates operate on spaces of 1 or 2 qubits, which means we have single qubit quantum gates and 2 qubit quantum gates. This means that quantum gates can be described by 2 by 2 or 4 by 4 matrices, but we do have quantum gates with more than 2 qubits. This Toffoli gate acts on 3 qubits. This figure represents the common quantum logic gates with the corresponding circuit form and the unitary matrices. Here the poly X gate and poly Y gate, Hadamard gate. These are the examples for single qubit gates, and control NOT or C NOT gate is a 2 qubit gate with 4 by 4 matrix. This is the matrix and circuit representation of poly X gate. This is similar to NOT gate in classical computing. This X gate acts on a single qubit and flips the value of that qubit. For example, X gate acts on ket 0, gives ket 1 state, and X gate acts on ket 1 state, gives ket 0 state. This means that applying the poly X gate is similar to a rotation of the state of the qubit of 180 degrees around the x-axis of the Bloch sphere. This operation is reversible because if we apply 180 rotation twice, we ended up with the initial state ket 0. This X gate is also called the bit flip gate, and this is the X gate applying to a generic state. Similarly, we have poly Y gate and poly Z gate. Poly Y gate also acts on a single qubit, and it equates to a rotation around the y-axis of the Bloch sphere by 180 degrees. This is poly Z gate. It also acts on a single qubit. Specifically, it maps 1 to -1 and leaves 0 unchanged. It does this by rotating around the z-axis of the qubit by 180 degrees, and by doing this, it flips the face of the qubit. This is one of the most important gates in quantum computing. It is called Hadamard gate. It acts on a single qubit and creates the superposition states. If the qubit is in 0 state, it will become plus state. If the qubit is in 1 state, then it will become minus state. This means that when the qubit is measured, it will collapse to either state 0 or state 1 with equal probability. Hadamard gate is reversible. If we apply Hadamard gate twice to a qubit state, we will get the original state. We will now look at a 2-qubit gate. This is control NOT gate, C NOT gate. The first qubit is known as control qubit. This is Q0 is a control qubit. And the second is known as the target qubit, is Q1. This gate is a conditional gate that performs an X gate on the second qubit if the state of the first qubit is 1. That means if the control qubit is in state 1, then it will flip the target qubit state from 0 to 1 or 1 to 0. If the control qubit is in state 0, then the target qubit state remain unchanged. Okay, now we will move to the second part of the presentation, which will introduce you how to access Qiskit. Qiskit is an open source development kit for working with quantum computers, and the primary version of Qiskit uses Python programming language. There are 4 elements in Qiskit that work together for interacting with quantum computers and simulators. First one is Qiskit Terra. It is called the Earth element because it is the foundation of Qiskit and provides a set of instructions to design quantum circuits. The second one is Qiskit Air. It provides a high-performance simulator framework for quantum circuits to run the program on local simulator or real quantum hardware. The third one is Qiskit Ignis, the fire element. This dedicates to do the calibration of real quantum hardware and error mitigation. And then the last one is Qiskit Aqua, the water element. It provides access to quantum chemistry, optimization, finance, and artificial intelligence. And when you need to start Qiskit, you have 2 options. The first option is to install Qiskit locally, which is more private and secure. For that, I recommend you to go www.qiskit.org and follow the instructions for your operating system. Here, I'll explain to you the second option, how to set up Qiskit on your computer using a virtual environment with Anaconda. Before I install Qiskit, I need Anaconda Python. So open a web browser and type Anaconda Python. And go to individual edition and click download. This will take few minutes, but if you have a Mac or Linux operating system, there are a few different steps, so I suggest you to go qiskit.org and follow the instructions. Okay, now my download is complete. Then go to the download folder and follow the instructions for your installation. Here you can pick any destination folder. Alright, after you complete the installation, close the window and go to Start menu and type Anaconda prompt and open that terminal window. Then type pip install Qiskit. This step is similar for all Windows, Mac or Linux operating systems. Okay, now Qiskit is ready to use. I'm going to use Jupyter Notebook, Jupyter Notebook to write some codes. It will open up a new browser window. Then go to New and create a new Jupyter Notebook. Okay, now I write a Python code to import Qiskit and check whether I installed it correctly. So type import Qiskit, shift enter. Now if you have correctly installed Qiskit, this line should execute. And then I would like to check the version. So I type Qiskit dot underscore underscore Qiskit underscore version underscore underscore and shift enter. And this gives you the output that has the version of it. This is what I have here. And now we can write quantum programs. First we write our code and then run it on a local simulator, and then we need to send it to actual quantum computer. For that we need to take an API token from IBM. This token gives the permission to use IBM quantum computer sitting in their lab. Therefore, we need to create an IBM account to get that API token. For that, first go to quantum dash computing dot ibm.com, and here you can create a new account and create new account. Okay, you can fill this information and create your account, and then go to your account. I'm going to log into my account. I already have an account. Okay, then go to your profile, click on account settings. Here you can see this is your API token. Click copy token. Then go back to Jupyter Notebook and type from Qiskit import IBM Q and shift enter, and then type IBM Q dot save underscore account and paste your token here inside single quotes and shift enter. Okay, so you won't get this message. This is because I have already entered this token before, so I am going to overwrite it. You don't need to do this step. Once this executes, we are ready to access IBM Real Quantum Computer from our computer. And I will type IBM Q dot load underscore account to check that I have access to their machines. Shift enter. Right, now it's ready to use. Now we can write our codes on our computer and run them on local simulator as well as actual quantum hardware by sending our codes to IBM quantum computer and get results back. Next thing is to write a simple quantum program and run it on both local simulator and actual quantum computer. This is the third part of my presentation. I have already discussed quantum gates and the Qiskit installation in previous sections, and now I will show you how to write a simple Qiskit program. To do this, we need to follow three major steps. First, we need to define our circuit. Then we run it on a local simulator or real quantum computer. Then the final step is to retrieve measurement results and view the results. To do this, I'm going to use my Jupyter notebook. Here I am assuming that you have already installed Qiskit and got the API token from your IBM account. And now we are going to write a simple Qiskit program. For that, go to New and create a new Jupyter notebook. And this is my first Qiskit program. And I need to import Qiskit. And also I'm going to import pyplot to plot all diagrams. Shift enter. Then I'm going to create a circuit with just one qubit and I call it circuit 1. You can give whatever name you want. Circuit 1. Here I put 1 because I am creating just one qubit. After you create a circuit, you can add gates. I'm going to add X gate to this qubit. So my circuit 1 dot. Now I need to visualize my circuit. For that, I type circuit 1 dot draw. Shift enter. It will give you this. I have my qubit and X gate applied to it. But if I type MPL here inside single quotes, I will have a better drawing. All of these circuit designing instructions are stored in Qiskit Terra element. And now I'm going to use state vector simulator to get information from Qiskit AI element. So I type backend air dot get backend and state vector simulator. Then type execute circuit 1 is the name of my circuit. This is to execute the circuit 1 on the state vector simulator. this object job will store the results. So then get various results out. I type result equal job dot result. Then get the state vector out of the circuit and store it in output state. I type output state equal result dot get state vector and the name of my circuit 1. Shift enter. And then I need to visualize the state. For that I import plot state city. It shows the state of the system using city heights. So from Qiskit dot visualization, import plot state city. Okay, now this is our output for applying XGate to a qubit state. By default, this initial qubit is in state 0. So we apply XGate and simulate the results, and here I got the real and imaginary parts, real and imaginary values of the density matrices that represents the state of the quantum system, which is 1, because we have applied XGate to quantum state 0. This is my output. Now I am going to measure the output. For that I need to create a measurement circuit to do measurements. This has both quantum and classical bits. So first I create my circuit and type, I will give it a name, measurement circuit mesh 1. One classical bit and one quantum bit. And then this is to perform the measurement. And then I need to visualize the circuit. I'm using MPL here for better drawing. Okay, this is the measurement circuit. Now we need to combine our circuit 1 with this measuring circuit. The combined circuit I call Q-circ1. Equals to my circuit 1 and my measuring circuit. Again, I need to visualize the combined circuit. So I type Q-circ1 dot draw. This is the output. This circuit is now ready to run on a local simulator or real quantum computer, but I would like to follow the same steps I have done so far to create a quantum circuit with 2 qubits and run it on a local simulator as well as the actual quantum hardware. Now I repeat the same steps, but this time I will create a circuit with 2 qubits to have entanglement. I open a new Jupyter notebook and import Qiskit and import Python. Um, I call my new circuit with 2 qubits. I call circuit 2. Here I put 2 because I need to create 2 qubits. And then I'm going to add a Hadamard gate on the first qubit. And also I apply control NOT gate, C NOT gate, considering the first qubit as control and the second qubit as target. Now I need to visualize my circuit. Here I have Hadamard gate on my first qubit and then I applied C NOT gate. Now I am using the state vector simulator. This is the same steps I have done for the 1 qubit circuit. And now I need to visualize the circuit, visualize the result. For plot state city. Output state. Okay, now I will create a measurement circuit. This is similar to what we have done before for circuit 1. I call my measurement circuit mesh 2 this time. This is to perform the measurement. Okay, for visualization, type S2 to true. Now, okay, this is our measuring circuit. This has both quantum and classical bits. I have 2 quantum bits and 2 classical bits here. Then I need to combine the circuit 2 and my measuring circuit, and I call the combined circuit as Q-circ2. Combine 2 circuits. And then I need to visualize the entangling and measuring circuit. Okay, now my circuit is ready. First, I will run this on a local simulator. For we are using CASM simulator for measurement type simulations. So I type backend. I use CASM simulator. And I need to execute this. And my combined circuit is circ2, Q-circ2. And here the short means number of runs. Then I need to get various results out. This measurement results give counts that resulted in different states. So I type counts. And my circuit name Q-circ2. Then I need to print counts. You can see the output here. 532 runs gives 0, 0 as my output state, and 492 runs give 1, 1 as my output state. Now I need to visualize these results. Visualization. Import plot histogram. plot histogram. Shift enter. As you can see here, this is the output from running on local QASM simulator. I have 0.520 probability of having state 00 and 0.480 probability of having state 11 here. Now the final step is to run this program on a real quantum computer. For that I need to import IBM Q. So I type from Qiskit import IBM Q. Then I need to load my IBM account. Since I have already entered my API token, I don't need to do it again. So I'm going to load my account. Now I'll give some instructions to run my program on actual quantum computer. Here I can see the status. First it's validating. Now it's in the queue. Now it's actively running on the real quantum machine and my job is complete. Now the last thing is see the output. This gives up to, and I need to print the count and plot it. Alright, this is the output from the actual quantum computer. You can see here we have 0.450 probability for state 00 and 0.466 probability for 0.11 state. Also we have a small number for state 01 and 10 as well. This is because of the noise of the actual quantum machines. Now you know how to write a simple Qiskit program and how to run it on a real quantum hardware. So you can make your own algorithms and try to run it on IBM quantum computer. I have come to the end of my presentation. If you would like to learn more about quantum computing or Qiskit, I would recommend you to go to www.qiskit.org, and this is the textbook for Qiskit programming. It's free and it includes very basic stuff as well as advanced applications. This textbook from Nielsen and Chang is also a very good reference for quantum computing and its applications. Also, if you are interested in quantum computing and quantum algorithms, you can join to Quantum Game Club and learn how to design your own quantum algorithms and applications. Thank you so much for your attention.